So the second part of Chapter 18, we'll actually look at the mechanism by which oxidation of amino acids take place, and then ultimately we'll move on into the production of urea in the future sections. But here we want to look at this removal of the nitrogen from the amino acid, generating the carbon backbone. So this is the way in which nitrogen moves in the system. Amino acids that you see up here at the top of the diagram, these can be any of the amino acids, will come in, and in the liver, what happens is those amino acids will be transported in, and the nitrogen, the amino nitrogen of the amino acid, will be transferred onto a molecule you're familiar with. This is alpha-ketoglutarate. Remember, alpha-ketoglutarate is a molecule in the TCA cycle. It is also the alpha-keto acid, because the keto group is alpha to this carboxylic acid. The alpha-keto acid of the amino acid glutamate. What that means is that if I replace the ketone with a primary amine on that carbon, I go from alpha-ketoglutarate to glutamate. And that's exactly what we're seeing here. This amino acid coming in has got an amine on that alpha carbon. We're going to generate instead a ketone on that alpha carbon. However, we're going to take alpha-ketoglutarate and we're going to generate the amino acid glutamate from it. So essentially, we're just converting all the amino acids into glutamate, and then we're generating their carbon structures for use in other things. So that puts everything in one common structure, and then that one common structure is what ultimately is used in the urea cycle, along with another molecule, another amino acid, aspartic acid, which we'll see in a moment. Now, there are various other ways that amino acids can come into the liver. It turns out two amino acids that are frequently transported in the bloodstream are alanine from the muscle and glutamine, which can come either in from the muscle or from other tissues. It's a very good way of transporting nitrogen. When glutamine comes in, it's transporting in nitrogen. It can be converted to glutamate because glutamine is just the amide of glutamate. And so you see this carboxylic acid has been generated into an amide. That's glutamine. It releases that amine and becomes glutamate, and then the glutamate, of course, can release its amine in the same as well. And then you also have that amine, which is all going into the urea cycle, or in some cases uric acid, but in the human case, the urea cycle. So that's a central reaction, is this exchange between a primary amine and a ketone, and these are called transaminases. So we had, as I said, a couple of things going on here. We had glutamine. Glutamine can move from one place to another. The way we deal with glutamine is we can either make it from glutamate, that's glutamine synthase, and then by essentially adding an ammonia to it, we generate that glutamine. This takes an ATP to drive it forward. That then can be transported on to the liver, and in the liver then you can regenerate the glutamine using glutaminase. So this is a common transport mechanism to get ammonia from one place to another without it being in the form of ammonia. So the one thing that I want to talk most about in this section is transamination. And this is there's a series of enzymes, transaminases, and they have a very important cofactor, pyridoxal phosphate, which is PLP here in the scheme. Pyridoxal phosphate will accept the amine group from a ketone and then put it back onto another ketone to form a new alpha amino acid. And so we want to see how that can take place, and we start to explore that on the next slide. This is pyridoxal phosphate. So you can see what we've got here. pyridoxal phosphate is an aldehyde. And of course, what you can do with an aldehyde is we can take that aldehyde and we can have it react with a nitrogen, which is a good nucleophile, and we can make a Schiff base. And so that's what we're going to end up doing with pyridoxal phosphate. Now, after we do that and do some other manipulations, we're going to leave the nitrogen on the pyridoxal phosphate, and then we're going to end up with pyridoxamine in the enzyme. So those are the two forms of the pyridoxal phosphate. Now, when we take pyridoxal phosphate and we put it in an enzyme, actually what it's going to do is it's going to form, as we'll see in the next slide, a Schiff base with this aldehyde. And that's how it's going to be held into the enzyme initially until an amino acid comes along and displaces that primary amine. So let's take a look at that. So here we are. This is the lysine in an enzyme right here. It's a transaminase. That amine's coming in, it attacks the aldehyde group, and it's going to form a Schiff base. This attack on the aldehyde group is just like the attack that we form a Schiff base in an aldolase reaction, where it comes in and it releases water, and we end up forming a Schiff base. In that case, that was to fructose bisphosphate in glycolysis. But here we're going to do it with an aldehyde and generate that Schiff base with the aldehyde, which you can see down here, the N+ double bond C, this imine group. So that's how we're holding it in the enzyme. Then we'll have an amino acid come in, and you can see that in this slide. Here's this amino acid coming in. It's going to take the place of this alpha amine this is a primary amine on lysa. This is an epsilon amino group, but it's the primary amine on lysine. This alpha amino group is going to come in, and it's going to take the place of that primary amine. And we see that here. So now the lysine has been displaced, and we have instead a Schiff base being formed between the incoming amino acid and the pyridoxal phosphate. So this Schiff base is now in an interesting position. Look at this here. You've got a carbon up here. You've got a nitrogen, then the imine type bond, the double bond Schiff base to this carbon. All we have to do is flip that, right? If I flip that, then this becomes the amine, and this is just a carbon-nitrogen bond. And then when I release it, when I go back again and add water and release it, what will happen is that this will become the C double bond O, and this will be the CN, right? Here I have this being the thing that if I release the Schiff base, this would become pyridoxal again. It would become an aldehyde. And of course, this is a primary amine. Once I flip this up, then what's going to happen is that when I release it, this becomes the C double bond O, and this becomes the primary amine. And that's exactly what you see here. We've now put the double bond up on top by the arrangement shown here, the electron rearrangement shown there. We can then do another rearrangement inside of the pyridoxal phosphate. This pyridoxal phosphate has a nice electron sink. We've seen this before. When we use a carbon-nitrogen double bond, imine type double bond with a positive charge as our electron sink, that's all we're doing. We're just pushing electrons into the electron sink. Now we're going to pull them back out of the electron sink and regenerate a simple C-N bond. But now we have our imine up here instead of down here. We add the water, and that releases our alpha keto acid. That goes off. Now, that would be the amino acid coming in that's giving up its amine. But now I've got an amine stuck on my enzyme. I'm dead, right? I can't do anything. But no, what I can do is now I can bring in alpha ketoglutarate, pick up that amine, go exactly backwards through this, and then generate glutamate. That's exactly what we were seeing in our diagram over here. That what's happening is this amino group is giving up its amine, forming the alpha keto acid. The alpha ketoglutarate then comes in, picks up that amine off of the pyridoxal phosphate, and forms glutamate. So just as we've seen here. Now it turns out that these transaminases can do other things. They can be involved in racemization of amino acids, changing the stereochemistry of amino acids. They can also be involved in decarboxylation of amino acids. So they can be involved in a number of different kinds of reactions. And you can see here that that's really quite simple. It's just a matter of breaking a different bond. Instead of breaking the bond with the hydrogen, you break the bond with the carboxylic acid and you release the CO2. So they're versatile enzymes. They can be used for a variety of different purposes.